what they call a rubber glove inflator. I never used one. Did you ever use one, Professor V?
We had them on the trucks, but it was easier just to test it the other way.
Mm-hmm. And testing it the other way was really just rolling it up by the cuff and squeezing it when it had full of air, and put your ear or face or nose up to your rubber glove. And you got someone in the trailer, don't you?
Might be up in my office, but I get it.
Okay. And we'll bring out some of the field today, show you how to test a set of rubber gloves and see how that's done. Yeah, it is very important. Every time you pull them out of the bin of the truck and get ready to put them on, to test them.
Correct.
And you check the date.
Do what?
And you check the date.
Check the date? Well,
yeah.
It's August the 31st.
Oh, smart ass.
No. How often do they get sent off and get tested?
Every 6 months.
Every 6 months, okay. Anybody else?
6 months.
Okay, Santee Cooper sent them off every 3. Once a quarter, we tested our rubber gloves.
Got him.
The maximum you can go is every 6 months.
Yeah.
And what that really means is that you're going to have, and we'll talk just a little bit on this. How many sets of rubber gloves did you have, Professor B?
I had 2 sets on my truck. I kept a set in my bucket, and I had another set in my locker just in case they got wet, or if I had a hole in them or something went wrong, I could always have my backup pair.
Right. And Santee Cooper, they worked what they called, they had dual distribution voltages. So you actually had 4 sets of rubber gloves.
Wow.
2 sets of 20 kV gloves and 2 sets of 40 kV gloves. And obviously, 1 set of 20 gloves and 1 set of 40 gloves were always off being tested. And then you had the 20 and 40 kV gloves on your truck that rode around with you, and you just rotated them every 3 months, rotated them back and forth to the testing facility. So they're very important to take care of. Make sure that you always have a rubber glove protector over the top of your rubber gloves. You don't wear a rubber glove just by itself. And keep them clean and in a safe place.
And also, guys, what we pushed hard was those protectors are on there to protect the rubber gloves, and it's so easy if you misplace one of your leather gloves to grab your protectors and use them for your leather gloves, but you don't never want to do that because you don't never want to risk, getting a hole in those or a cut on them or something like that, because that's the outer protection for your rubber gloves.
Let's see. I'm trying to bring up an image, which is pretty pitiful. They don't show any ones with protectors on them. That's a pretty decent one. I'm going to try to share again to see how bad this bombs out, if it does at all.
There you go.
See that okay?
Yep.
Yep. All right. We're really not going to get in this morning as far as classifications and whatnot, which you'll see there's different. That's orange, yellow, red, white, and green. Those are for different voltages that you can use these rubber gloves on, but these are just the plain ones. All right. And you can get them sized to your hand. Not that this is a different size, hand size, as far as the height of them is concerned. But you can't get them as far as if you got a big hand, bigger in the hand and finger area and smaller in the hand and finger area. I will let you know this is kind of an indicator here of voltage. The longer the cuff, the higher the voltage, the longer this goes up your arm. Okay. What do you do if you have a set of defective rubber gloves? If you tested them out there in the field, you found out, oops, these are bad. What do you do with them?
Destroy them and throw them away immediately.
That's a good answer. Go ahead and cut the fingers out of them immediately and throw them away. Let your supervisor know that you did that, but do not let them ride around on the truck. And somebody else might pick them up, or you might pick them up in air even after you've tested them, and that's a bad thing to do. Don't take them home and think that, like this, let's just say this is a 20 kV glove that I got my mouse over. Don't take them home and think, well, I can use this on 12240 or something on a lower voltage. Once they have a defect in them, they need to be destroyed.
Yeah.
Okay, anything more on rubber gloves?
I'm just going to add in there that that's your PPE, and that PPE is personal protective equipment, guys. You don't really want to be passing around your rubber gloves to somebody else on the crew. They've got a set, unless it's an emergency now. But I mean, that's yours. That's what you're putting your hands in every day. You want to maybe wash them regularly, but inside of them. But I mean, that's your protection for you.
Right. Let's see. Use that one.
There you go.
See a picture of a bucket truck?
Absolutely.
There you go.
The
All right.
Duke.
Is it Duke?
Yep.
All right. Congratulations.
Yeah.
Gentlemen, you'll see this gentleman in the bucket truck here. Now, does anybody know what parts of the bucket truck are insulated? I'll take that as a no. The outside bucket itself has insulation. There's a liner in the bucket that has insulation. Kind of hard to see in this picture, the lines though. There's a line right here and a line right here. This entire area is made of fiberglass. That's insulated. There's a line here and there's a line here. This entire area is made of fiberglass. It's also insulated. Now, this is an industry standard that's out there for all fiberglass products that are in utilities. Sticks, fiberglass crimping machines, fiberglass cutters, fiberglass on booms. These are all rated to 100,000 volts per foot. So they have an insulation value of 100 kV, 100,000 volts per foot. So if I have a, let's say that boom section right there is 15 feet. This one at the top. How much insulation do I have between the bucket truck and this part of the boom? 15 feet times 100,000.
1,500,000.
1,500,000 volts. Okay, that's just this section of the boom. You also have 100 kV per foot through the bucket, and this small section right now, we would say, Professor P, about 3 feet.
Yeah.
So you're looking at potentially about 2 million volts worth of insulation you have between yourself, if you make contact with the conductor, and the ground. Guess what the bucket truck operator manual is going to say inside of it as far as working out of the bucket? Am I now, since I am 2 million volts worth of insulation, am I now able to touch a live conductor without any protection on?
No,
Why not?
because that'd be a stupid decision.
Well, that's part of a good answer, yeah. All right, no truck manufacturer, even if you bring it off the lot brand new, this thing drives in the service center, you just brought it from Altec, it's an Altec bucket truck. They're gonna have in there right in the front page, this aerial device is not to be used as an insulated device. It's kind of weird. They will not stake your life as far as putting down a warranty to say that any type of the insulation in this boom will be an insulator between you touching a conductor and ground. What is the only barrier that you have control of that you're able to insulate yourself from either a conductor up here making contact from one conductor to another, or from the bucket truck to ground? What is the only thing that you have? What was our safety meeting about?
Rubber gloves.
Rubber gloves. Okay, that's the only thing that you have control of. That is your personal barrier between voltage and its path to ground. So that's how important rubber gloves are. Even fleet manufacturers will not put a warranty, and they'll put a special note inside the first page of that manual inside the bucket truck, not to be used as an insulated device, even though
Professor Shoemaker,
Yes, sir.
I got a quick question. Do you have, as far as your input on, what would you say? Do you have more accidents on as far as linemen on climbing or in a bucket truck?
Good question. Great question as far as the safety meter is concerned. When you refer to an accident, do you mean anything that requires medical attention?
Yeah, anything as far as would you say, because I know like you can have hydraulic malfunction, stuff like that, as far as more incidents, do they come from actual climbers or bucket malfunctions and stuff like that?
No. Bucket truck operation and bucket truck use is very, very safe. It used not, bucket truck, and Robbie, you can chime in here too. Bucket truck manufacturers and to the company that had them were not really good. And it's like I told you before, the weakest part of any kind of truck that you have out there in the industry is the turntable. You would have breakdowns. Sometimes you would have bucket failures where the bucket itself would break off the end of the boom. Those have pretty much gone away completely, haven't they, Rob? Yeah, that's gone away. Plus, the organizations now take very, very good care. And I know my old manager, Neil James, out there is very, very strict on keeping these trucks in great working order. The buckets, no, I would not say so. As far as accidents are concerned in the industry that cause injuries are probably, and I have probably investigated again, I've done it a couple of years ago, are falls. And not only falls from poles, but falls from ladders or being up elevated somewhere, and cuts. Using knives and tools and whatnot and getting cut. Those are the most prevalent. Electrically, there are very few actual electrocutions in the industry where voltage passes through a person and the person is electrocuted. But there are some cases, not regular, but cases do happen where you're going to get what they call an electrical flash burn. Now, electrical flash burn is where a conductor has touched ground, no path has gone through you, but some conductor or something's happened up here on the pole and a flash occurs. That flash is 6 times hotter than the sun.
Yeah.
And then you get an immediate flash burn on the employee. Those do happen out there in the industry if the employee is not protected. And we'll talk more about safety. Who's their safety person for tomorrow?
Yeah. Who is yours?
I don't know.
Who do we have today? Justin?
We had Justin Dale Bailey.
Yep.
Yep.
He was this morning. He did rubber gloves. Who's tomorrow?
You're one of your guys?
Yeah, I had to relog in because I'm not.
And while you're looking that up, I'm just gonna say, just like that picture of that truck, I had one of the guys that I worked with after I left over in Sumter. They were working storm trouble in a bucket just about like that one that you showed. And it was raining, which he shouldn't have been handling the energized conductor in the rain anyways, but he did. He grabbed it. He actually had his raincoat. His sleeve was over the outside of the rubber glove, not tucked inside of it. And it actually tracked through across his rubber glove, across his raincoat, through the bucket, the ground, and it held him there, locked his muscles up, and he couldn't move. The guy in the bucket next to him took his fiberglass stick and pushed him off of the conductor. And everything just lined up perfectly for an accident that evening. And what happened was they determined was, like Professor Shoemaker said, there's a bucket liner in there for protection as well inside of that bucket. Well, evidently, after they'd been drilling, we've got these long drill bits and it's got a point on the end, and they drilled a pole and they stuck it in the bottom of the bucket, and that tip melted through the liner, so it caused a hole, and with the rain and the dirt in the bucket and down the boom, it tracked over the ground. So it can happen. It's a rarity, but things you have to be really careful in those situations, and you'll learn the safety practices for the company you go work for, on what you can and can't do. But he made a mistake, and he actually put his hands on he had his rubber gloves on, grabbed that energized conductor. It was 13,200, and it tracked over and got him. He survived, no problems. He had a couple little burns, but it really didn't amount to a whole lot where it could have. It could have stopped his heart and could have been more serious than it was. So just kind of have to follow your safety rules as you go along. There's hundreds and hundreds and hundreds of safety rules out there, guys.
Yeah.
And just need to, and they're all from accidents, most of them.
That's true.
That's how they come up with safety rules.
All right, Cole, I see you made in here from the text. Cole Templeton, Tanner Carpenter. You here?
I think I saw him laying in the bed. There he is.
Tanner,
Yes, sir.
you're in the safety meeting for us tomorrow morning. You got 2 things you can choose from here now that we're talking about rubber gloves and electrical flashes and whatnot. You can do electrical arcs, or you can do FR clothing, that's fire retardant clothing. So take your pick for tomorrow, okay?
Yes, sir.
All right, take a shower, put your shirt on.
Yes, sir.
All right. Okay, anything else on the safety aspect this morning as far as rubber gloves and whatnot? Good subject.
Yep. Excellent.
Okay, I'm going to jump in the book. I'm back in the math book. Get video started. There we go. Yep, we're back in the PPM for math book. Practical Problems in Mathematics, Unit 11. Find your page here in just a moment. That's page 60. And they're talking about the addition of, we're talking about decimal fractions, and I really just like to call them decimal numbers. This is going to be pretty simple. We'll be able to breeze through this pretty quickly. And if you look on the Unit 11, how to add, the example on page 61, the addition of a decimal fraction, it's, bring up my screen right here. It's pretty much the case in the addition of decimal fractions. Losing that black thing. And is all you have to do when you're working with decimals is keep the decimals in line. So pencil this, that. The example they give, 4.0563. Plus 0.9800, so 0.9800, oops, and 14.008, that's as far as we'll go, 0.0008, yep. In addition, just keep your decimals in line and move the numbers to the correct area where they need to be, and add down. So that punch into a calculator would be your answer. I'm not going to go through the answer right now. That's just the way to get it done. Keep your decimals lined up addition wise, and you'll be able to take care of decimal numbers. All right, same thing in subtraction. You just go through right here and subtract as long as you keep your decimal numbers in line and do subtraction on this equation, you'll be fine. So we're gonna move through some things here real quick because we're getting ready to come up to percentage, and percentage is gonna be a little time for us. All right, move to Unit 12, subtraction. I'm just gonna run right over that. All right, multiplication of decimal fractions. All right, who knows how to do those? I'm going to use the example in the book. 8.650 times 3.5. Does anybody have a simple solution of how you do multiplication of decimal numbers? I was getting ready for somebody to say, "Hey, yeah, just put in your phone calculator." Has anybody heard of? Go ahead and just don't worry about the decimal. Just worry about how many decimal places there are. 1, 2, 3, 4, and multiply the number as is.
Yeah.
Can anybody speak?
See.
Yes.
Okay, so that's the way I do it. I'll take 8, 6, 5, 0, and 35, and I'll count 1, 2, 3, 4. I'll just multiply those two numbers together. Has anybody got that solution?
Let's see.
It'll make me break out a calculator. My hands are full now.
Let's see.
302,750.
302,750. All right. How many decimal places do I need to move? 1, 2, 3, 4. 1, 2, 3, 4. Is that correct?
I guess.
I guess. You guessed correctly. 3.5 times 8.650 is 30.275. 1, 2, 3, 4. 1, 2, 3, 4. There you go. That's multiplication. All right. And remember, on the test, guess what you can do? Because I can't see you.
Calculator.
Yeah, use your calculator. Okay. Unit 14, division of decimal fractions. It's the same concept. 19.44 divided by 3.6. Count decimal places, throw it in your calculator, divide, add your decimal places back. All right, now we're going to get into some meat and potatoes. Percent and percentage on page 86. All right, to learn this, and Professor Vermelin had this picture up the other day. Okay. Get rid of that. Need to move so many windows around, it's pitiful. All right, share screen. Okay. Now you should have that transformer nameplate up on the screen, correct?
Yes, sir. Yes, sir.
All right, we're going to start talking a little bit of the terminology of electricity going on here and things you need to know as far as volts, amps, and watts. Even though it's in the next chapter, you need to know it now, or at least the basic parts of it, to be able to do calculations on what you see in the window here. So, don't be afraid to chime in. We're in the learning process here, so if you know the answer, go ahead and give it. If you don't, if you give it, don't be afraid to give a bad answer. It's okay. All right, what are volts? If you had to give it a term or like a short definition of what volts are, what would you say?
A measurement of power.
No, measurement of power is watts, but we're getting to that point.
Electricity.
Electricity. Is it electricity watts? Is it electricity amps? Is it what kind of electricity?
I don't know.
Okay, that's okay.
Amp.
Go ahead. Who said something?
Amps.
Amps is part of the equation, but we're just going to be, we're going to break volts, watts, and amps out. We're going to break those out today to give you the definition of what each one of those are. Volts is electrical, and this is just plain and simple, pressure. Electric pressure. Okay. And I kind of like to use this when I'm using this definition. We'll just go ahead and go through these and I'll do a drawing for you. All right. Now, amps. Who said amps?
Me.
All right. As far as electricity is concerned, the full scope of everything, what are amps?
Is what something pulls?
What was that answer?
Is it what something pulls, like the amount is used?
That's a load. That's a load, correct. And the load is using amps. But if you had to define amps, how would you say, what are amps in the world out there? What are amps?
A unit of electrical current.
Current. Okay. So we've got current, which directly relates to amps. I like to put it this way: electric flow. It's the flow of electricity. Well, I've got the missing C's today, don't I? All right, it's the flow of electricity. All right, and finally, watts. Oops. Now, who said, somebody already answered part of this one.
Measurement of electricity. Something like that.
We can measure electricity in different, we can measure volts, we can measure amps, and we can measure watts. Those are all three different measurements. Somebody said power. Who was that?
It might have been what I said.
Okay. Watts is power. That's the actual consumption. Okay, that's the actual electric consumption. Got keyboard dyslexia today. Yeah. All right, that's actual electric consumption. I like to give this analogy that goes along with it right here. And it's kind of, I want to say weird. Let me start up another instance of paint. There we go.
Professor Shoemaker.
What's up, buddy?
Would watts be like the amount of power though?
That's the measurement of the watts in the amount.
Okay.
Right? Has anybody ever gone to the store and picked up a light bulb? Does it have a watt rating? Have you ever paid attention to that?
Yes.
All right. So say if you pick up 100-watt bulb, how many watts is that bulb using?
100.
There you go. Okay, and 75 and 50. So that's the actual power consumption. Whatever the piece of equipment, say a light bulb or a motor or your laptop or your phone, whatever, your phone actually uses watts. That's the actual consumption of both voltage and amps. So let's you still see my paint stream up blank, right?
Yep.
Okay, so let's go to the volts part. All right, I like to think of it in this way. I'm going to put a water line out here. Okay, I'm going to cap off the end. Then I'm going to put a pump over here and start pumping water on this line. All right, will this line have pressure?
Yeah.
Once I start the pump? Yeah. Okay, so there's going to be pressure in the line. All right, that's the same thing volts do. If I have a generator and I put voltage on a conductor, and I'll make my conductor a little bit smaller. Nothing's attached to the conductor. It just comes down here and stops. Do I have volts on the conductor? Generator?
No.
Yeah, I'm putting volts on the conductor. So that volts are electric pressure. My water pump and water lines, water pressure. That's all there is to it. Depending on what my pump size is, I can pump at 120 psi. So I have 120 pounds of pressure on my pipe. My generator is 120 volts. How many volts of electrical pressure do I have on the power line? 120 volts. Does everybody get that concept? I'll take that as a yes. Okay. Same situation here. We're going to talk amps. Okay. Here's my water pump. Here's my water line. Okay. Here's my generator. Here's my conductor. Okay. I'm going to take the cap off, and water's going to start flowing out. Once I have done that, once I put the water line to use, I have, what do I have going on down here? Flow. All right. The flow of water through the line is the same thing that happens here in electricity. Do I have to have pressure to have flow?
Yes.
Yep. So amps and volts must be present. I've got to have pressure. I took the cap off. Now I have flow. When I had the cap on, all I had was volts. When I took the cap off, now I have volts and amps because of flow. Same thing with the generator. I'm going to come down here. I'm going to hook my light bulb to it. That's a sorry looking light bulb. All right. And then I'm going to put a neutral and ground over here. All right. Do I have to have pressure on it? Yes. All right. Once I turn the light on, do I now have flow?
Yes.
Yep. Now I have amps. All right. We'll use this same picture right here. We've gone through all three except one. We've done volts, got to have pressure. Once I take this off, I'm going to put a paddle wheel over here. This is kind of weird. All right. And on my electric side, I've got volts and amps. Now I've got flow that I've turned the light on. Once something is being used, all right, I've got a use or an output. Both here and here, I've got output from the lamp. That is watts. Lots of calculations are going to come off of this, gentlemen, but I want you to know what these three things, and they're very important to us right now, what volts, amps, and watts are. If I turn the light off, you got a switch right here. I'm going to click it off. Do I still have electrical pressure on the line, volts?
Yes.
All right. Do I have amps?
Yeah.
I turn the switch off.
Yeah, because it's still, no, never mind. Nope.
No, once I turn the switch off, there's no path for me to flow, and really flow is not needed. So I don't have amps anymore. Do I have watts now that I turn the switch off?
Nope.
No, because the light's not doing anything. Turn the switch on, click, volts still present, amps are now flowing, watts are being produced. I've got output. Now there's two types on the light bulb itself. There are two things being produced inside the light bulb. What are those two things? Wow, that's an nasty looking light bulb. What's it giving off?
Light.
Right? Put your hand
And
over it. Put your hand, heat. There you go. light and heat. So two things are being produced in the light bulb itself, light and heat. And that measurement, the measurement of both the light and the heat being produced is measured in watts. There you go. You get a 100-watt light bulb, it's going to be brighter and hotter. You get a 10-watt light bulb, not going to be as bright and not going to be as hot. So that value is going to be lower. Any question there? And now's a good time to ask before we move on about volts, amps, and watts. Volts, electrical pressure. Amps, the flow of electricity. Watts, the consumption and use of volts and amps together, the consumption of electricity. All right, let's take a break. What time we got here? 10:09. Let's make it nice even number here, 10:20. We'll see you guys back in about 11 minutes, okay?
All right.
All right. Sounds like somebody's having some breakfast. Robbie, I got to meet with Becky Boone at 3 o'clock this afternoon. He's not back yet.
Professor Shoemaker,
Yes, sir.
you said the climbing gear and all that normally takes about 4 to 6 weeks.
Yes, sir.
TM4, appreciate it.
Have you heard from Mark Jones?
Yes, sir. He sent me an email last week just confirming everything was right.
Okay. Remind me to bring that up when everybody gets back.
No problem.
Okay, so it's 10:20. We'll go ahead and get restarted back here. I promise we'll get back to the math part. You need to know these things, though, before we can really apply to the electric utility information and know these things before we can start doing math on what we're talking about here. And just to touch base, the volts, amps, and watts definitions there, the short terms, which I kind of like to use out there in the world. If anybody is not square on those, you need to let me know. Volts, electrical pressure, amps, electric flow, watts, the consumption. All right, let's talk a little bit about conductor. All right, can anybody give me a short definition of what they think a conductor is?
Something that conducts electricity.
Mm-hmm. All right.
It takes the electricity.
It easily conducts electricity. All right. When you say electricity, TRI, electricity, volts and amps. So I can easily transport volts and amps over a conductor. You guys got any examples? What are good conductors out there in the world?
Gold.
Gold is low down the list.
Copper.
Copper is probably one of the higher ones as far as the utility is concerned. We're not going to make lines out of gold.
Aluminum.
Aluminum. All right. So copper was the old standard out there in the old times. It's become so expensive that now most of the industry uses aluminum conductor. So you'll see, I mean, it's not to say that you're not going to go to work and not see some copper. There is still some out there in the world. But most of the time, your new installations are going to be all aluminum. So aluminum is the preferred nowadays as far as new construction. So those are good conductors out there in the utility world. Now, what is the best conductor in the utility world? And it is used in switches and contact points. That would be silver. Silver is the best conductor. All right, let's talk insulator. All right, what's a good definition of an insulator?
Like keeps it in.
All right, so if a conductor easily conducts electricity, an insulator prohibits.
Yeah, keeps it out. You know.
Yeah, prohibits the flow of what? Volts and amps. All right, so it's gonna not let electricity flow through it. Give me some good examples.
Rubber.
Rubber's great.
Plastic.
Plastic,
Fiberglass.
not so great. Fiberglass is great.
Wood.
Wood does have some insulation values to it. It's not the best, but it does. So
Plastic.
plastic is poor. Now let's narrow it down to the industry. What do we use in the industry?
Rubber.
We don't have rubber insulators on this pole.
Shit,
Ceramic or
yeah,
something like
glass. No.
Well, glass was used in
Porcelain?
old days.
Mm-hmm.
All right. The most prevalent nowadays is porcelain. And what did they call the other one, Robbie? It's composite. Yeah, it's composite. It's kind of a, I don't want to say rubber and I don't want to say plastic. It's kind of like a fiber composite, flexible fiber composite that they use. And we'll show you, that's what you're seeing when you see the dead ends on our poles out there, those long insulators.
Yeah.
It's called a composite dead end.
We call them a polymer dead end.
Polymer, there you go. P-O-Y-L-M-E-R, polymer. Thank you very much, Robbie.
Uh-huh.
All right. So we know the two things, conductors and insulators, what their purpose is. Now, is there a perfect conductor? And what I mean by perfect, it does not prohibit the flow of electricity at all.
No.
Can you hear me? Not sure if my microphone is working. Paul Hughes, I do not hear you. No, there's
No.
not. Now I do. All right. Is there a perfect insulator?
No.
No, there's no perfect conductor. There's no perfect insulator. So there is going to be resistance in a conductor, even if we're using the best one, to the flow of electricity. When I say flow, that pertains to what? Amps, okay? And there's no such thing as a perfect insulator. There is going to be an electron flow, even though minute, over this insulator. That's why we have the conductor here, we use a porcelain insulator. There's a certain amount of distance. Why don't we use, and some companies do, I don't like it that much, why don't we use steel cross arms?
Because they're heavy.
There are actually lighter steel cross arms than there are these wood ones.
Because they're conductors.
Never mind.
Right. What's fully included here by design engineers and the people that you've got the value of insulation of the insulator plus this entire distance of wood. That's an insulator also. So that's both added together plus the pole. So that's added into the equation also. The thing I definitely want you to remember, though, there is no perfect conductor. There's no perfect insulator. All right, finally, we get down to get some math going on here.
Can you put them notes in Ramon?
They'll be on the video, but I can put them in Remind. Sure.
Thank you.
Put them in D2L2. How's that sound?
Yeah, thank you.
You're welcome. You're welcome. All right, so now let's get to work on this transformer right here, and we're going to figure out on the nameplate what's really going on and do some calculations on it. Okay. Let's talk kVA here. You'll see kVA 15. Now, I want you guys to understand, as far as alignment is concerned, out there in the world, kVA equals watts. Now, if you were to say kVA of a transformer to an engineer is going to say, well, you're not accounting for temperature, you're not accounting for power factor, all these other variables out there as far as watts is concerned. As far as alignment is concerned, the good rule of thumb here is this transformer is a 15 kVA. It's able to produce or feed 15,000 1500, 15,000 watts. Slide that over just a little bit. kVA, 15. 15 kVA means it's able to feed 15,000 watts. Well, what does that mean? All right, let's try this out. I've got my little ball field out here. I'm going to put some lights around it. I'm going to put 15 1,000 watt lights. What size transformer do I need?
That one.
That one. It's able to produce 15,000 watts. Okay. I have got, yes. Let's see, I've got my little outside pool. All right, and it's heated. And my heater needs 20,000 watts for the heater. Just for the heater. What kVA do I need to feed that?
20.
20 kVA. There you go. You get the concept right now. Whatever I am feeding, watt-wise, determines the size of the transformer, 15 kVA. Now that's loose. Remember that. It's good for alignment. Engineer's probably going to talk you down. Don't worry about that. You're a lineman, not an engineer, I hope. All right. What's the high voltage of the transformer?
7,200.
7,200 volts, phase to phase. And we talked about this before when we did the calculation. If we went from one wire to the other on the primary side, that would be 7,200 volts times 1.73, 12,470. And what's the low voltage coming out of the transformer? LV.
120
120
over 240.
120, 240. So that's definitely what we want to use as far as in our house and, you know, maybe a small business, but that's the typical transformer output voltage for all your residential customers. All right. Okay. Now that we're in the book and we're up to percentages, you'll see this right here, and this is on the nameplate of all transformers. Let's see if I can circle it for you. I can find my little doodah. Bang. Let's draw a shape.
Yep.
That number right there. And you'll notice, see if we can move this thing around. There you go. You'll see right in this picture right here, percent IMP. The IMP stands for impedance. Everybody know what impedance is?
I can look it up.
No, take it literally. I mean, you guys.
Kind of like a resistor, maybe.
Well, you're close. If Robbie were to come running at me and he wanted to knock my block off, and I put my arm out and held him back,
You stop him.
I'm stopping him. Yeah, I'm trying to slow him down so he doesn't take me out. All right, that's impeding him. All right, whoever said resistance, very close to it. The thing with resistance is, in electronics and electricity, I have to have a resistor component to do resistance. Impedance is really directly related to conductor right here. What did we say before? Is there a perfect conductor?
No.
All right. So every conductor has what they call impedance, the resistance of electric flow without the resistor. Now, inside a transformer, there's windings inside a transformer that are so long and they're made of copper that, of course, electric flow is going to be impeded because it's not a perfect conductor. So in this transformer, it's a 15 kVA, but it's impeded by 2.6%. So it's really not a true 15 kVA, and temperature does affect it. You can see that temperature going on there. We'll talk about that later. So let's talk a little bit of math right here. And this is the way I do it. If you have a different method, please let me know. I'll take 15,000. That's the kVA of the transformer. And I convert my impedance to a decimal number. You move the point over 2 places. 0.2, 0.02.
I got it.
He kicked right up in front of me.
Okay.
So I'll say it again. 15,000, 15 kVA. All right. And I'll convert my percentage into a decimal number. Move over the decimal 2 places. 1, 0.2, another 0.026.
Oh.
15,000 times 0.026. Who's got their lucky calculator out?
Mhm.
Nobody?
Yeah. 390.
390?
Yep.
All right. 390 is the answer for that right there, but we want what we're trying to determine here. And when we ask questions, we'll ask, well, what's the voltage impedance? I mean, what's the wattage impedance? Or we'll ask, what's the true kVA of the transformer? It's impeding it, so it's taking it away. 15123 minus 390 equals
610.
14610. Okay? So now you know the true wattage output of the transformer with the with the impedance included. That's how you compute it. Now, is there anybody out there that does their percentages differently? Okay. The thing you just need to look out for is the question itself. Why did that go away?
It's gone.
Yeah.
There it is.
All right. Now that you know what impedance is, that means it's prohibiting the flow of electricity. I know that's a subtractor. If I had something I needed to add, or it was a percentage boost, then I would add that 390 to 15,000. So that's, really discount and interest is what you're talking about right there when you talk those two numbers. Just watch out in the wording of the question. Am I taking something away, or am I adding something to it? All right, so your guys' turn. Stand by. Let's see what we can find here. That's the one we just used. We've used this one before. No, not that one. I didn't want that one. I wanted the ABB. There you go. Okay, so I'll let you all figure this one on your own right here. All right, what size kVA is it?
200.
200 kVA, so 200,000 watts. What's the impedance in percentage?
4.21.
4.21. Calculate for me, please, what the true kVA of this transformer is.
191,580 kVA.
So 200,000 times 4.2, 0.0421 equals what?
I got 8,420.
For that number right there.
Shit. Oh, what?
8,420.
That's what I got.
Okay.
That's what I got.
200,000 minus 8,420.
$191,580.
Thank you. There you go. All right. Is this in kVA?
No, that's all the way up.
That's
Now,
all the way out. That's in just plain watts, right? How can I convert this back to kVA?
all you have to do is, if you want it in kVA, just do the 200 instead of doing it at 200,000, and it'll give you the answer in kVA.
So 200.
Yeah, I did 200 times that.
200
And then-
times 0.0421 gave you 8,420.
No, you change the answer in it. Whatever you get
Explain it out
times
for
that.
me. Explain that out for me.
I did 200 times 0.0421, and you get 8.42, and then you subtract that from 200, and it gives you 191.58, I believe.
All right, that's
Okay.
completely legal. I'm glad you said that. I mean, that's completely legal. If you want to do it in that fashion, you can do that fashion, and you will.
Why don't you just divide it by 1,000?
Excuse me?
Why don't you just divide it by 1,000?
What, this number right here?
Yeah, 191,580.
I just come right here, and what I would say is 191.580 kVA. I just move over 3 decimal places. There's multiple solutions. That's what I'm going to get at, guys. You guys that are doing math, what you feel comfortable with is fine. All right, so he just went and got an answer of 8.42 and did the 200 minus 8.42 and did that minus, he just never used the 100,000s part, which is okay. I just figured it all the way out with 200,000. And when I got done with my answer, I moved over 1,000, 10, 100, 1,000 decimals. So it's 191.580 kVA transformer or kVA actual. As long as you come up with the answer and you feel good about it as far as your math processes, I'm a happy camper. How about you, Robbie V?
Yes, sir. All the way. Actual.
Okay. All right. Anybody want to do one more? It will be a test question.
I would actually like to do one more.
Sure. That is not a utility transformer. That's a current transformer. Okay, kVA is 150. Might be a little bit hard for you to see right there. And HV total. Wow, that is really hard to see.
Where's the impedance?
Right here.
1.25
1.25.
or 4?
5.
Okay.
Yeah, we'll go with 5, just for calculation. 150 kVA, 1.25% impedance. Engaged.
1,875.
1,875. That was your first calculation?
Yeah.
Okay, so that's what you need to subtract from 150,000, depending on your math method.
148, 125.
So yeah, if I was asking for the final answer, what's the true KVA of the transformer? The answer was
148, 125.
148, 125. If I tell you to convert that to KVA, you're going to do what?
14.8.
Move over 3 decimal places, 148.125 kVA. You're feeling pretty good about that?
Yep.
Hey, can I ask a quick question?
Is that a question or concern? Okay. All right. So let's go back to the original one we had. Nope. There we go.
Professor Shoemaker,
Yes, sir.
is there any way we can do one more?
Absolutely. Let's see what this one does for us.
I'm just trying to write it all down. That way I make sure I have it if I need to go back and look at it.
Oh, why did that? There you go. All right, cool.
25.
KVA rating,
25.
25. Convert that to a regular number, 25,000. Impedance,
4.5.
4.5%. Here's me. Nobody talked yet. Robbie, you got your calculator handy?
Yes, sir.
25,000 times. I'm going to change my number to decimal. Point, what was it?
That's 4.5.
0.5. All right. 0.045 equals
1125.
1125.
Right.
All right. 25,000 minus 1125 equals
23.875.
23.875. You already converted in KVA for me, didn't you?
Yeah.
All right, KVA. Nice.
And the number that you get whenever you take the 25,000 times 0.045, you get the 1125. The 1125 is what?
The 1125 is the solution of that math right there.
That's the 4.5%.
Right, that's the 4.5%. I converted 4.5, the percentage, into a decimal number right there. That gave me 1125. Because I'm impeding the flow of voltage and amperage in this transformer, I'm going to take it away from the actual transformer rating, 25,000. Minus the 1125. There's my final answer.
Simple.
Good with that?
Yes, sir.
All right, excellent. Thank you for asking the question. It was a good one. Okay. My computer just kicked me.
Uh-oh.
I'm back now.
All right, Bubba. Glad to have you back. All right, we'll go through a couple more things here and take another break on the transformer nameplate. We did talk before about be sure that when you pick up a transformer out there in the field and whatever you need to get as far as that concerned, as far as off the yard, don't trust what's painted on the transformer. Usually they'll have information painted on the front of it, like company number and kVA, and sometimes they'll actually do the voltages on the transformers.
Right.
In fact, I like to use all the time. There's that one that I had before, Robert. It had the dual voltage.
Yeah, that's the one I was looking for.
Now we'll go with one of these.
Is it right there in the middle? Where the 50 is on the pole there? Okay. Go right there. You just passed it. Right? Is that 15? No.
PCB free.
No. Okay. Couldn't read that little writing.
It's got a ton of information on it.
Yeah.
All right. You'll see in this picture right here, and there's different manufacturers and whatnot. There's a lot going on in the front here. Some companies will actually put the input primary voltage and the output secondary voltage. They'll stamp that on the front too. What size transformer and kVA is it?
50.
50. Okay. And all that other information. Am I going to trust that?
Mm.
No.
No. I mean, it's a good indicator where to go and what to pick up. But always go back to the nameplate and check that nameplate out and make sure that that 50 matches the actual kVA and the nameplate before you pick it up out of the field and head off with it. I think that probably the worst thing you can do. I give a little short story here. Happened to us a good while ago. Is I don't know if anybody knows where Defective Plantation is. It's close down there to the Waccamaw River where it comes out down there in Georgetown. And our service center was in Myrtle Beach. So that's a good haul. And we had a crew that went down there and they had a transformer. It was a 500 kVA that went bad. And they needed somebody to come in and pick one up out of Myrtle Beach and drive it down to Defective, which is probably a good 40-minute drive. Plus all the other stuff to load it up and whatnot. Well, the guy goes into the service center, gets a helper, they get a boom truck, and they load a 500 kVA transformer up on the truck, and they haul it down to Defective. Take the old one off, put the new one on, close the switches in, and the lights are real dim. So they start checking voltage, and they check the voltage coming out of the transformer. And it's like, for this voltage right here, it's like 40 volts base to ground, and it's about 80 volts base to phase. And they're scratching their head. Oh no, we got another bad transformer off the yard at Myrtle Beach. We're gonna have to get another one. Well, guess what the problem was? They brought a transformer that should have been 7,200 12,470. They got the right size, 500 kVA. They brought a transformer down that was 19,900, 34,500. The primary voltage was meant for another voltage. Guess what you got to do? You put that transformer back to the service center. You load another transformer back up, get everything changed back out. And I mean to tell you, you pretty much get chewed out harshly for burning about 2 hours of everybody's time plus the customer because you didn't look at the nameplate. If the crew is down there and they're sending you information to pick a transformer up and it's not everything that you need, hey, I need a 15 kVA transformer. Is that all the information that you need?
No.
Robbie, this is Scott. I need a 15 kVA transformer. What's your reply going to be, Robbie?
What's your secondary voltage?
Right, and?
Your primary voltage.
What's your primary and secondary voltage? Yeah. All right. Ask those questions while you're out there in the field and don't get stuck with
Yep.
somebody giving you misinformation or no information at all. Okay. Let's take about, what time is it now? 10:54. We'll make it 11:05. Let's take
Cool.